So, welcome everybody. I'm delighted to particularly welcome Michael Lord, who was a analyst for the climate change committee as an industrial decarbonisation, and also speaking this evening will be myself and Simon Daniell, who both of us are from Hope Valley Climate Action on the Energy Group. I'll let people say more if they want to when they introduce themselves, but let's get straight into it. And Simon is going to talk first.
Right. Thank you. Right, the topic tonight is about using less cement. Well, using less cement really came up because the main part of HVCA did a meeting with Michael Lord and somebody else to talk really about carbon capture. And we felt the other thing we ought to try and do is talk about the other side of it, which is how we can actually use less cement and therefore produce less CO2. So let's start with the basics.
This meeting is being recorded.
Right. Goodness, where's that coming from? So Portland Cement was...
everybody who's not themselves.
Portland Cement was first named in 1820 by a chap called Joseph Aspdin. He named it after Portland stone, quarried from the cliffs of the Isle of Portland in Dorset, and what's been used to build things like St Paul's Cathedral and the British Museum. Its composition really is it's made from limestone and clay, which are heated in a kiln to form something called clinker, and they then grind that with gypsum, and this is what clinker actually looks like when it's come out the kiln. Now, concrete is a durable stone-like building material, which we all know. It's got some cement in it, but the cement forms a binder for the sand and the stones, and it hardens with time. So if you look at the bottom here, you can see that cement is 15% of the concrete, but it's 80% of the cost and 90% of the embodied carbon. So you get the raw material, you make your clinker, you crush it with gypsum to make the concrete, you put the concrete in with the aggregates, and you transport it to make a building. So that's how it works. And there's carbon produced at really all these stages. So the problem is that the elephant in the room is the clinker, which is 88% of concrete's carbon footprint. And the production of Portland cement is responsible for 8% of all global CO2 emissions. And it's increasing. At the moment, we make 4.1 billion metric tons, but construction is projected to increase partly because of rapid urbanization in the global south, so that we'll be building equivalent to a New York City every month for the next 40 years, which is a horrendous thought, actually. Okay, here we're importing more cement, which means effectively that we're exporting our CO2. And it's been suggested that it should be carbon tariffs on imported cement to protect the UK cement producers as they try very hard to decarbonize our cement production in this country. So what are the solutions? Well, we could make less cement. We can do it by substitution or recycling or upcycling or increasing the efficiency of the supply chain. We might reduce that by cause 22% reduction in CO2. We can make it in a better way through existing processes or electrification or feedstock innovation. We might get 25% reduction that way. Or we can have new ways of making it with novel processes, etc. And the other necessary steps to actually decarbonize cement is to electrify it rather than using fossil fuels to power the kilns. Carbon capture and storage, those two look to be 45%. As we decarbonize electricity, that's going to save 8%. And then the other problems we've got are that the standards that we have currently in place don't really fit with the new ways of cement and concrete. And you have to remember that when you're going to solve this problem, you have to deal with local demand. So it's not only what's going on in this country, it's what's going on in other parts of the world with what they have as feedstocks, what their policies are. And it's very good if you can actually put the feedstock near where you're actually wanting to make the cement, make the concrete and do the work. Because of course there's CO2 produced by the transport. So these are the ideas where we can go from 2020 to 2050 to with the increase in the production and how we might do it from efficiency, from process emissions, from bringing remaining emissions to net zero, and then electricity, which is pretty well decarbonized at the moment. Now, carbon capture and storage particularly has been talked a lot here in the Hope Valley because of Breedon and the plans to capture the carbon, shove it down a pipe and stick it under Morecambe Bay. It's not a silver bullet though, as you could probably realize. There's a high capital and operational cost to it. There are logistical challenges to get that carbon dioxide to the sea and store it. There's all the hurdles of planning and public involvement. It's difficult to do on large scale. At the moment, I think there's only one, and Michael may correct me, there's only one plant in Norway producing low CO2 cement. There's another one planned for the east coast of this country. And then always the worry is, will that carbon dioxide actually stay stored? So how do we use less? Well, the first thing is, let's reuse the buildings or make them last longer because they've got a huge amount of embodied carbon in them. And the embodied carbon is the whole life cycle of the building, from extraction of all the materials, putting them together, etc., etc. And so the other thing we can try and do is optimize the structural design. So we use less concrete. If we allow longer setting times, we don't need so much cement. We can choose the most efficient mix. And you'll see later there are different things bringing it in, gives the concrete different properties. We can use different materials. Buildings have been made out of mud or wood or stone. So here we are in the Far East, a mud building. I worked a time in Africa, and this is how they built things there, a sort of frame with mud piled on, or you can just pile the mud up. Here's a local one, a printed mud building. That's hot off the press. You can print with plastic, but you can print with mud. And of course, wooden buildings we all recognise, very common, long-standing. And this is Castleton. Here we are with a lot of stone and on the buildings, another way of reducing it. And in fact, with our traditional buildings here in the Peak District, we put them together with lime mortar. And that actually is very much more low carbon than using a cement-based mortar. And the other advantage of lime mortar is as it cures, it actually captures CO2, and this is called carbonation. Now, we think about what else we can use. So these are supplementary cementitious materials. There's an awful lot on this slide, and we will send out the video later so you can do this at your leisure. But I'll just pull out a few things. So you can swap 20 to 50% for the cement. You can use fly ash from coal-fired power stations. Well, we don't have any coal-fired power stations anymore, do we? So that might be a bit of a problem. Blast furnace slag. It gives an excellent resistance, but that's got availability issues. There's silica fume when you're making silicon metal. Gives you a high-strength, low-permeability concrete. You can use low-grade calcined kaolitic clays to go with the limestone, and you can lower the temperature. So these are all ways that we can lower the emissions. And then also there are feedstocks like basalt, which don't actually contain haven't any carbonate in them. So that will reduce the emissions. And then we come to these, what they call pozzolans. Now, everybody knows that about Roman concrete. I think that the Pantheon has lasted 2 millennia while our modern bridges crumble after 50 years. They used a volcanic ash called pozzolan, and that could reduce emissions by 67%. And there are industrial pozzolans like glass powder, rice husks, incinerator ash. So these are all things we can add in which will reduce the amount of cement we're using. We can also use other fillers to produce a low clinker cement. So we can increase the finely ground limestone content, which can displace clinker. There are modern cement mixers which changes the percentage in the mix of the cement. And there's some good early results on this, that they are standard. But again, we come into the regulations and the standardization issues there. We can use alternate binders. As you remember, I said that cement is the binder that binds the stuff together to make the concrete. We can use other binders which are not cement. And again, this is a busy slide, but just to pick out some of the things, they are geopolymers which come from pozzolans, but they aren't pozzolans as such. And these you treat them with an alkaline activator, and that can reduce the carbon footprint. There's magnesium oxide which could be used. The advantage there is some of these absorb carbon dioxide as they harden, but there's a supply chain issue there. Ferox from recycled steel dust and silica from ground glass, they trap the CO2 during the curing process. So they can become carbon negative ways of producing concrete. There are biomass derived binders to make a bioconcrete, and you can also put in agricultural waste, bioash, algal char. These are very experimental. This is a very complex, rapidly developing area, and I find it quite hard to really do it to justice. But I'm hoping that I'm giving you a flavour for what's going on to try and decarbonize the cement uh, supply chain. Now, carbon capture and mineralization. This is an interesting one. This is where you actually inject CO2 into concrete while you're making it. The CO2 reacts with the concrete and forms calcium carbonate. So the gas is being embedded in the concrete as a mineral. The advantage is it strengthens the concrete, but you can't really do it on site. But you can do it when you're making precast concrete products. And there's quite a lot of those made. You think of the concrete pipes, all the units that go in to make flooring, etc., etc. So that's another way. Another clever thing they've done is they've taken lime aggregates and then coated waste with minerals with captured CO2. And that's another way of reducing or capturing the CO2 to reduce the CO2 that's being produced. And then we've also got bio-based and recycled alternatives. You can see there's a lot of work going on here. Hempcrete, great for insulation retrofitting. It's not really structural, but it's a great insulator and it's good for carbon sequestration. Timbercrete using sawdust, again, limited to bricks and paving. And then what do you do with all the old concrete from the buildings you do actually knock down? So you can recycle that, either using the aggregate to recycle that instead of it going to landfill or other ways, or you can actually produce the concrete down to a fines, which is a binder. So these particles will help create reactive particles, which you can use to partially replace the clinker or add to the other cementitious materials that you're using. So it reduces the amount of virgin material. And then there's other research going on. Graphene's being looked at, bacteria for making concrete that self-heals from its cracks, electrochemical conversion, which will lower the temperatures required in conventional cement manufacturing. So again, other ways of reducing the amount of energy that and CO2 that goes into the production of cement. And if you want a sort of overview of the whole thing, I would recommend this article from the Rocky Mountain Institute. This is the link to it, which will be on the video.
Great.
So,
well, thank you very much, Simon.
Stop sharing.
You ran over time slightly, but I got so interested I forgot to keep an eye on the time. Thank you, very interesting. What I suggest we do is go straight on to mine and then Michael, and then have questions and discussions at the end. So save your questions. Simon, can you give me a time check halfway through? If you remember, which I didn't, and I'll go straight on to mine. So I'm going to talk about three alternative building materials, three types, rammed earth, and this has been used in the Centre for Alternative Technology building in West Wales. Straw bales, and that's being used, and thirdly, using wood, and this wood building is an 18-storey building at the University of British Columbia in Vancouver in West Canada. So the Centre for Alternative Technology was in a former quarry, slate quarry in Montgomeryshire, Wales. It basically uses rammed earth for the walls. The earth is compacted into 10 centimetre layers, and they used a handheld pneumatic ram to do that. And the walls are 1/2 metre thick. The earth walls, they say, have huge thermal mass, which helps keep the building cool in summer and warm in winter. They produce a 4-page fact sheet, which is really dense. I can't possibly hope in the talk here to cover all the information in it, so do go and look more if you'd like. So that's used for this big round building, which is the lecture theatre, and there's the inside of the lecture theatre. But at the same time, they also put up other buildings for which they used earth blocks. And earth blocks, as well as being a good warmth insulator, also act as a good sound insulator, which they use between teaching spaces and between bedrooms. The outer render outside both the earth blocks and the soil rammed earth is hempcrete, which Simon mentioned, which is made from hemp and lime. Now they did also add 15% cement, and they did also make the foundations with cement, use cement in the foundations. The Centre for Alternative Technology, being on the former slate quarry, they had sufficient low-grade slate aggregate on site to make the building site level, but they made the foundations of ordinary concrete reinforced with steel to achieve the required strength and stiffness to withstand the movement of the underlying ground. They said concrete made from lime, not cement, or even unreinforced concrete would not have been suitable. But they did drastically reduce the embodied carbon by making the concrete from half cement and half ground up blast furnace slag, one of the things that Simon mentioned. So basically I was talking about the walls from rammed earth and bricks rendered with hempcrete, and the foundations they did use concrete in, but by using half cement and half ground up blast furnace slag they reduced the embodied carbon. The roof is made, though, from sheet stainless steel, from recycled steel. I was surprised in that choice, but they say it's infinitely recyclable at the end of a building's life, and it lasts for a long time. They also use insulation in the roof, and they use cork for insulation in certain key places, such as under the first floor terrace, which you can see in the right-hand picture. And they also used some perlite in places in walls and ceilings and under the ground floor slabs. And perlite is a volcanic rock that puffs up when heated. They designed the ventilation so that they didn't need air conditioning to limit the amount of mechanical ventilation, but they do use a little bit of mechanical ventilation in the lecture theatre and in shower rooms and toilets, which I can imagine shower rooms and toilets are places that do need a bit of electric fans. So this is the straw bale building. They used no cement in the building at all. They made cement-free foundation by using stone with a lime mortar. Now, it was on good load-bearing soil, but they didn't dig any trenches, they only removed the topsoil. And then above that foundation, they made the floor is insulated limecrete, and it's above clay balls with a layer of silicon-coated clay balls to create a damp-proof course. And this is the first modern building of this type, but actually it was quite common in older Yorkshire buildings that were built before cement existed. So they had some interesting discussions with the planning inspector, but they managed to persuade him and went ahead. The walls are load-bearing straw bales with a lime plaster externally and a clay plaster internally. And the roof is cedar shingles. Here, sorry, I should have moved on. Here you can see the straw bales being constructed, and as you can see, while it was being constructed, they used wooden supports, and you can see there the stones in the foundation. And then here's the top of the wall where they're about to put the roof on. And then that's the finished building. When first finished, the first pictures were, I think, after a year or two when they planted the stuff. So then the 18-storey student building, it was the tallest. It's, as I said, University of British Columbia. It's on their campus, and it was built for accommodation for students so that they could live on campus instead of having to travel from somewhere else. At the time it was built, it was the tallest building in the world made of wood. Since then, others have been taller. It's now the 5th tallest building. But also, there's 5 other structures that are taller that range from telephone masts, wind turbines, and other towers. It turns out that wood is a low conductor of electricity, so it's quite good for telephone towers. This was made from what's called mass timber, which is cross-laminated timber. And if you're not familiar with cross-laminated timber, do ask me in the questions, which provides strength and stability. Concrete was used in this building for the foundations and the ground floor and 2 main stairwells. But if you know about West Coast Canada, the whole of the west coast of North America is on a fault line, and so it's what's the word, geologically unstable, and so although there might not be an earthquake in this year or next, probably sometime in the life of this building there will be. If you look at the history, they're travelling northwards, so there haven't been any as far north. There haven't been major ones as far north as Vancouver, but they probably will be while this building's still up there. Now, cross-laminated timber is fine up to 10 to 12 stories without any concrete, even in severe seismic regions. But as this is 18, they went for a hybrid solution. Once the design was, it took just 9 weeks to build. That's 2 months plus a day or 2 more, whereas a conventional building of this size typically takes between 6 months and 2 years to build, so it was fast to build. They don't say, I haven't found out what they used for the roof, but as I say, they did use concrete in the foundation. I did some research about avoiding concrete foundations in wood buildings, and it depends on a variety. Oh, I'm suddenly getting an echo. I hope that doesn't persist. It depends on a variety of things. soil subtype, the geological movement, and all of that can depend whether you need normal foundations or deep foundations, which use piles, usually steel piles, but sometimes of timber. But, as I say, buildings up to 10 to 12 stories, even in seismic areas, can manage without concrete in the foundations. So, because I want to talk about using wood for buildings and other structures, and I'm going to cover these points. There's 5 of them, and I'll cover them one by one. So let's go straight on to environmentally friendly. A green building clearly has a wood building clearly has a hugely lower carbon footprint for all of the things that Simon was discussing about not needing to make cement and the chemical transformation of that and so on. It's greener also because it's lightweight to transport compared to the aggregate and concrete and so on for conventional buildings. You can prefabricate the timber in factories so that you're only taking the parts of the wood that you need, the beams and all the bits and the pre-laminated all cut to size. And so that also cuts down on waste. The bark and unsaleable bark, the unusable bits, the wood chips can be made from can be used for various things, from mulch to biofuels. Wood is obviously a renewable resource, you can keep on growing it, and it's good insulation. I need to rip through this, but you can see that a standard brick, this is the lower values the better. So standard brick 0.8, reinforced concrete 2 to 3, and cross-laminated timber 0.13. This is made from spruce. Hardwoods would be even better, but even so, cross-laminated timber is 6.5 times more thermally resistant than bricks and 15 to 24 times better than reinforced concrete. So it's just vastly better as an insulator, and it's long-lasting. It lasts hundreds of years, and it stores the carbon the whole of that time. So it's a carbon sink. It's not just carbon neutral. And even when the building's no longer needed, the wood can be repurposed and recycled, and even after it's come to the end of its life, as it breaks down naturally and is not harmful to the environment. So for all these reasons it's green. Other qualities, it's got great strength and structural performance. It can carry heavy loads, so it can span wide spaces so that buildings can be designed to have wider but larger spaces with fewer supports than with concrete ones. It's lightweight, so fewer foundations are required, and as I mentioned, cheaper found for transporting. It's got elasticity, so it can absorb a certain amount of stress without cracking, which makes it suitable for earthquake zones and other seismic areas, and is longer lasting than other building materials. Obviously, if water gets in from the roof, it can rot, but if you keep the roof in good condition, wood can last hundreds of years or even thousands of years. If you think of places like York Minster with its wooden ceiling. Now, fire. People often say, but isn't it a fire risk? I wasn't able to find conclusively what makes it not a fire risk. So I'm unclear whether the timber needs a special treatment or if it's the nature of the wood. As you know, in California there's 2,000-year-old trees that have survived hundreds of fires in their life, or if it's the fact that it's cross-laminated. If you've ever sat by a campfire, you'll see how fire likes to burn along the grain of the wood rather than across it, and with cross-laminated timber having all the crisscross structure, that could be. But the building in Vancouver was designed, they did some calculations and they reckoned, one of the things that wood buildings do is they char, and the actual charred charcoal slows the rest of the burning. And so they've done a calculation that building in Vancouver people would have 2 hours to get out of it, or firemen to get in to rescue people. And they've also designed it in a way so that the fire shouldn't spread ever to the whole building. It's been done in segments. Wood is a good sound insulator. It absorbs echo and does something called soften the sound. That doesn't mean make it quieter, but it changes the quality. So wood is often used in auditoriums, music studios and meditation spaces, and is good in just general buildings too. It's got low electrical resistance, which is why it can be used for telephone masts and other towers. And then land use issues. Now, no one is suggesting that we should be building wooden buildings from old growth forests. We need to preserve all our old growth forests, both temperate, boreal, tropical and so on. But we have lost vast areas of the world, have lost their forest, and growing wood for timber, for buildings, is often better than other ecological purposes. People, plantation forests have a reputation for being low in biodiversity, but that's what you compare it with. If you're comparing using the land for forest or for arable crops, whether it's sweet corn, wheat, sunflowers, potatoes, field vegetables or whatever, they have a lower biodiversity than plantation forests. So now, land use is a complex issue, and if you want to discuss it further, do ask me in questions. But it's not as bad as one might think. And it's easier for construction. It's quicker. It's quieter construction compared to concrete buildings, which makes it suitable for inner city areas where building needs to go up and the neighbours don't want a lot of noise for a couple of years. Because of the prefabrication, there's less waste, and it's quicker, and it also has design flexibility. And here is some really wacky design flexibilities of wood buildings, as well as that skyscraper. So it's really versatile. So in conclusion, I would argue wood is an outstanding current construction materials, be far, far lower carbon footprint and have many other benefits. Okay, well, we've run over, but I hope that's been interesting. Let's have Michael next.
Thanks, Zee-Zee. Yeah, thanks for that, and thanks to Simon. Both interesting presentations definitely from my point of view. So good evening, everyone. I'm Michael Lord. I've spoken to your group a couple of times before in person. As I think Simon said, until recently, I was at the Climate Change Committee where I led on industry. So cement was part of my bag, but only really a small part of it. It was in a job a few years ago where I kind of really got to grips with cement, where I was head of research for a small climate NGO in Australia called Beyond Zero Emissions. And then weirdly, the first report that I produced was about cement. So I've got it here actually. I had to pick it up to remind myself what I'd written. So it's called Rethinking Cement. So it's nearly 10 years old now, and I guess cement still isn't, it's not top of the climate mitigation agenda, but then there really seemed to be nothing on it. Now there's things like that Rocky Mountain Institute research that you mentioned, Simon. So it's been a while since I really got to grips with this subject, and I think some of my knowledge is out of date, but not as out of date as I'd like it to be, because things haven't moved quickly enough. It's still a big problem. Actually, a lot of Simon's presentation reminded me of the stuff that I got to grips with when I first started learning about this, and also Zee-Zee's, because we had a section on timber in that report that I just shown. But I definitely, broadly agree. Last time I came to speak, I was asked to speak on carbon capture and storage. So, and I remember during that, I felt like I was like a defender of carbon capture and storage, but it was just kind of what I was asked to speak on. But I'd say broadly, there are just three ways to get rid of the emissions from cement, which is carbon capture and storage, or carbon capture and use, which Simon touched on, using less of it, which was the focus of yours, and just then novel ways of making cement. It basically boils down to those things. And I don't think anyone mentioned why cement of all industrial processes is kind of the trickiest. Perhaps you did actually, Simon, but it's worth saying again that it's unusual because while it's a very high temperature process, most of the emissions come from the process emissions of decomposing limestone, so about 2/3 from that. And the rest is from burning fossil fuel for the energy. Both of them are really tricky problems. Like theoretically, you could electrify a cement kiln, but it's about the kind of hardest industrial electrification project you could set yourself. No one's gone beyond a kind of paper-based feasibility study of electrifying one of these at a large scale. The feasibility study, it was in Sweden, it found that it was possible, but they didn't then say they were going to build it. It would require huge amounts of electricity. There's a few kind of major challenges with it, kind of any solution with cement, and it applies to some of the things that Simon and Zee-Zee have mentioned. So one is, can it really replace? So when we talk about replacing cement, we're talking about replacing concrete, really. And, concrete has become ubiquitous for a reason. Like, it's super strong. One thing I didn't mention is, I don't think you mentioned it, it starts off in, a liquid form, fresh concrete from a concrete mixer, which is really useful for, pouring it into foundations. You can make it into any shape you want. It allows you to put steel within the concrete, which, most concrete has steel within it to give it that. Otherwise it wouldn't have tensile strength, and it would succumb to bending pressures. So yeah, and then it's really strong, and it basically lasts forever. The reason bridges might fall down after 50 years isn't really the concrete, it's the steel within it that's rusting. But the concrete lasts forever. So, things like hempcrete or other things like that, they I love those projects, but they don't produce the kind of strength that concrete does. It's measured in MPa. Concrete generally would have to have a strength of like 20 MPa. MPa is the measure of pressure it can resist, or it might be 40. There's no way something like a straw bale or hempcrete has anything like that kind of strength. So, which is why you didn't have examples of 20-story mud brick buildings or something. You might be able to go 1 or 2 stories. And also, most concrete is actually like at ground level or below ground. It is for foundations, for very tall buildings, and for things like ports and airports, HS2, I don't like HS2, but anyway, if you're going to build something like that these days, it'll be built with concrete. So yeah, can it really replace concrete for most reasons is one question, and then is it going to last, the decades? And what's your evidence that it is going to last? These are all the challenges, all the things that were thrown back at me when I was, originally talking about my report and the solutions that I saw to decarbonising cement. And then a really big one is there enough of whatever the raw material is? So we can have replacement cements, but one reason Portland cement has caught on around the world is that it's made from limestone, and limestone is available in many parts of the world. Like, it's very widely distributed. You guys live in an area of limestone. And so there's kind of loads of it all over the place. I think Africa is one continent with a bit of a lack of it. But apart from that, I believe it's pretty much everywhere. And we use 4 billion tons of cement. So you need, like massive quantities of whatever your replacement is. So these are some of the challenges. What else? I was going to say another thing about wood. So I used to also give presentations with the picture of the Vancouver building. And there's a few other tall buildings which you mentioned built from wood. I love those. I've been in a couple of tall buildings made from wood, and they are fantastic. If I was doing the report again 9 years later, I would look into the actual embodied carbon related to building with wood a bit more, because since people have started to suggest it as an alternative for environmental reasons, there have been some studies, it's called life cycle assessment, of using timber, and some of them have found that it's worse than using concrete. Now, I'm not saying they're true or not. I've never looked into it in enough detail, and life cycle assessment always is very susceptible to the assumptions you make. So I think they make assumptions like, that the land isn't a plantation, it's probably, left to go wild or something like that. It's very susceptible to that assumption you make. But there are definitely studies out there by reputable people. There's a guy called Tim Searchinger who does research into food, who has produced studies saying timber is, at least from a carbon point of view, is worse than concrete and cement. I'm not saying that's what I think, but I would just be more reluctant these days. I used to be a big champion of timber buildings. I'd be more reluctant, maybe particularly in Britain, where we don't necessarily have the space to have lots of plantations. When I originally did this, I was talking about Australia, where they've got, they could have a lot more forest in Australia, and no one had really noticed, to be honest. I think I had some statistic where they could build a certain percentage of building, and they would need plantations only covering the area of their current chickpea acreage. So I found, it wouldn't need much there, but here it would need a lot more. I'm probably sounding a bit negative about some of these things, but I am really positive. I'm probably more positive about finding alternatives, so novel chemistries. I would just call them cements, even if they're not Portland cement, rather than binders. So there are quite a few. I shouldn't even say novel, actually. There are quite a few different chemistries for making cement, and the one with the longest heritage is geopolymer cements, it's a term you don't see much anymore. There are some geopolymer cements coming out on the market, but people seem to have dropped the term because it sounds a bit weird and like it's made of plastic or something. But the other term for them was alkali activated cements, but they don't tend to really mention that either. So they've got a different chemistry. They tend to use the supplementary cementitious materials that Simon mentioned, so fly ash, slag from steel making. The other big one is clay, or calcined clay, which Simon mentioned, and you mix them with an alkali activator, a liquid alkali activator, and that's how you make your cement. And they date back to the 1950s. In fact, early on in the Ukraine war, you might remember Mariupol was in the news, and they defended a steel plant. Some of the early geopolymer buildings were built in Mariupol in the 1950s because they had so much of this the slags from the steel industry, and the USSR were one of the countries that developed these geopolymer cements, and they built buildings that were still standing until 3 or 4 years ago, when I think they have unfortunately been knocked down. So there's a long history with these cements, which is geopolymer cements, which is a real advantage when you come to talking about replacements, because you can point to their durability. There's actually evidence of it, which is fantastic. And someone mentioned in the chat, I'm not sure whether it was in reference to this, but there's a plant started up near Wrexham, a company called Material Evolution, and they're aiming to produce about 100,000 tons a year. So not as much as like the Breedon plant in Hope Valley, but quite a lot of cement, which will be geopolymer, which is significantly lower emissions. It doesn't require high temperatures to make. The highest emission part of it is making the alkali activator. So that's really great, and they're going to make it, I think, mostly with steel slags. But to me, the real future is to work out how to do this with clays, because clay is one material which is like limestone, that is very widely distributed in the world, and there's loads of it. And there's loads of it, for example, at the edge of existing quarries and mines. So land that's already been disturbed, you wouldn't necessarily always have to start a new quarry or mine. So if we can work out how to make cement with clay, I think that will be that will be a major part of the answer to decarbonising cement. I'll mention, maybe I'll stop in a minute for questions, but I mentioned Material Evolution. There's another couple of companies that are worth mentioning. One is Cambridge Electric Cement. So this is a UK startup. So what they do is they take recycled concrete, which would normally, if anything happened to it at all, it would be like a road base or something. It would like broken up for a low value use. They put it into an electric arc furnace, which is how we recycle steel. And it acts as something called the flux, which is something that they need in the electric arc furnace. And normally they use limestone. But what is produced is very similar to cement, but with most of the emissions removed. So that's under active investigation now at the largest electric arc furnace in the UK, in Wales. And then there's a US company called Sublime Systems, which is has developed an electrochemical way of making cement. So they use electricity and some kind of clever electrochemical process, which I can't explain. But the raw material is a silicate rock. And again, they produce something that's chemically identical to existing cement, but without the emissions, which is pretty amazing. Whether there's that much of the silicate rocks, enough in the way that there is of limestone and clay, I'm not so sure. But anyway, I think it's got real potential, and Microsoft and others are building things with their product now. So just about oh, good, somebody knows about Material Evolution. You can tell us more about that. Yeah, achieves price parity with Portland. Yeah, there's no reason why these things shouldn't achieve price parity with Portland cement, especially when they're at scale, because the raw materials are like wastes or clay, which isn't particularly expensive. So what I think needs to happen is there needs to be some incentives to to get moving on this. At the moment, there's basically no incentive to reduce the embodied emissions of a infrastructure project or a building. In Europe, they're introducing embodied emissions standards. So the embodied emissions are the emissions that go into the making of the building. I can't remember the name of the directive, but there's an EU directive which is, first of all, requiring buildings, large buildings and infrastructure projects to measure their embodied emissions. And then they will, from, I don't know, 2028 or something, they will actually have to achieve standards, which is at the Climate Change Committee is what we recommended every year to government. But, they're considering it. So that would go a long way. And then public procurement. So preferential purchasing of things like, the material evolution product and Cambridge electric cement once it's fully commercialized would be fantastic. Right, I'll stop there so we've got time for discussion.
Well, thank you, Michael. I see one hand up already. Because we're more than one screen, please use the reaction button to put your hand up. So if you click on that heart that's a reaction, it has various reactions, but the second bottom one is raise hand. And as I say, because we're more than one screen, that's the most efficient way to do it today. Tim, would you like to start with your question?
Thank you very much. Well, I've got 2 or 3 actually, but I'll condense them. On the subject of wood, I agree with Michael's point. My son in New Zealand makes his living helping sorting people out whose houses were built of wood and have rotted. Nothing was said about using steel rather than concrete for structures. And I would like a comment from that, please, Michael. Can I have a comment, please?
Yeah, sorry, I was just muted. Also, I was thinking just on the rotting wood, the type of cross-laminated timber and other engineered woods are much more, I imagine those buildings in New Zealand are just sawn timber.
They would have been.
So engineered wood would be much less susceptible to the rotting. Okay. Yes. So that's one thing. On the steel, I imagine, I mean, again, it's only for those above ground things. And as I've said, most concrete is used at ground or below ground. So the steel building wouldn't replace that, but would it be lower emissions? I don't know. I mean, steel.
I'm thinking about bridges. I mean, did you mention HS2 and all those vast concrete structures?
Yes.
Which probably upset everybody here. How would the use of steel for those bridges have compared in CO2 terms with the use of concrete, I wonder?
Yeah, I don't know the answer to that, but as you know, steel is not particularly lower emissions either. So yeah, I'm afraid I don't know the answer, but I don't think you would get to any lower emissions, and it would probably be a lot more expensive.
Thank you.
Mark, can you ask your question, please?
Yes, hi, I'm Mark Johnson from Morelands Climate Action in Staffordshire. Obviously, we have the same issues that you're facing. Thank you first for 3 very well structured and useful presentations. So very focused on sort of the tech bit of it. I'm interested, given that we're all against a ticking clock. How do you re-engineer a building trade? Let's just concentrate on the UK. How do you re-engineer a building trade, reskill a building trade that is already extremely old, stressed, etc., doesn't really even have the skills infrastructure? How do you get the building regs in, to replace, especially as you get further away from Portland? How do you get the building regs in time? How do you do all that kind of stuff? I mean, I guess the implication of my question is I don't think that's feasible in the time scale for the UK on its own, let alone internationally. So maybe some comments on that.
Michael, can you comment on that?
Yeah, sure. I was just waiting to see if anyone wanted to comment. It was something when I was talking a lot about cement, and I would talk to the construction industry in Australia, which is somewhat similar. It was something that came up a lot. So on the skills issue, I mean, if you're using a different type of cement, it will work differently, and there'll be different things that you have to learn. But you're still basically using cement and concrete. I mean, there's a company in Australia I haven't mentioned that they use geopolymer cement, and they built Australia's newest airport. They built a port, a wharf, various things. So they've used their own cement, geopolymer cement concrete on that, and they've just trained the workforce. You know, there are certain different health and safety issues because it's quite alkaline and things like that. But they're not like a sort of go-getting startup. These are sort of like salt of the earth rural Queenslanders, if that means anything to you, and they've learned how to use this. So and that's really without too many incentives. So that can be done. I think the standards and regulation is a bigger issue because it moves so slowly. But there has been a geopolymer standard in the UK, a British standard for quite a while now, but it's not the kind of key cement and concrete standard. But now the industry is trialing. What they need to move towards is a performance-based standard, so a standard that doesn't actually basically specify that it has to be Portland-based cement. And there is something now called British standards like Flex 350 or something like that, which is the industry is working towards integrating that into the current standard. So while it does take a long time, a lot of the work has been done. So we're not far away from having that standard. So I think both of those things are solvable.
Thank you. This is where having you here to know some of this wider picture is really valuable.
I'm having to dredge my brain for things I used to know.
Martin, would you like to ask your question? And once people have asked their questions, if you put your hand down, that would be great.
Right. Right. A couple of comments, really. One is that we need to be worried about fire in high-rise buildings. Granted, there have been a number of cases of large buildings with quite considerable loss of life due to the fact that once a fire gets hold, things which are considered to be perfectly safe suddenly start burning. Grenfell Tower is an obvious example. So we need to be careful about that, and also the means of evacuating buildings. The other one is one of the great things about reinforced concrete is that it has very high tensile strength. I can remember when I was in Norwich and they were replacing the wooden roofs above the concrete, above the stone vaulting. They couldn't replace, well, there just wasn't wood available to replace the A-frames, and they replaced them with concrete, with reinforced concrete, and they actually managed to pull the walls of the nave in by several feet, because they'd spread out over the centuries because of the wooden construction. So there are reasons for wanting to use reinforced concrete.
Certainly, and it does need careful design, but the structural engineer, I found an article by the structural engineer who designed the Vancouver building, and he reckoned that they'd done all the modelling for fire, and that, as I say, the building would be able to they'd have 2 hours to evacuate, which should be plenty for normal circumstances. Even if somebody's completely disabled, the fireman could get in, get them out in that time.
Well, it does require that people notice the building is on fire, which at Grenville Tower they didn't.
As I said, I'm not an expert, but the structural engineer reckoned it was safer than something like a material like Grenville Tower was made of, which once it caught, it just flared up enormously. As I say, I'm not an expert. I don't know if Michael has anything more.
I definitely wouldn't claim to be an expert either, but I was just trying to find a quote actually about that Vancouver building, because I used to have in my presentations a quote from the Vancouver. I couldn't find the quote, but anyway, Vancouver fire chief who said it was the safest tall building from a fire perspective in Vancouver. And as I remember the same as you, that it's the fact that cross-laminated timber is in layers, and in a fire the first layer would char, and that would actually prevent it from burning further, or at least, for long enough. So I believe they can be built safely, but also not an expert.
Thank you. But thank you for making these points, Martin, because I think it is important to hear both sides of the debate. It's good to hear the points you said. Do you want to come back at all, or shall I go straight on to Andrea?
Well, just to say that the issue with Grenville Tower was that the fire officers thought it was safer to keep people in their flats rather than to evacuate them, which is why there was such a considerable loss of life.
Yes, that's a good point. One needs to have clear evacuation procedures, which I believe they have for the Vancouver building. But as I say, thank you for raising the point. Andrea, do you want to ask your question, please?
Yes, thank you. I was just interested in what was it, Daniel, at the beginning, talking about lime mortar and saying that that would produce. Sorry, was it Simon? Sorry, that it produces a lot less carbon than cement production, and I'm also aware that lime mortar is used in for Grade 2 listed buildings. And so I was just wondering whether to reduce the amount of carbon that cement factories produce, like Breedon, etc., that they could swap back to using more lime mortar and do, because it's a perfectly feasible working, material. So what does Michael think to that, please?
All right, yeah. Thanks for the question. I don't know loads about mortars, but what I know is that the amount of mortar required is tiny compared to the amount of like proper cement that is used in concrete. Lime mortar, I guess you've still got to create the lime, right? Which is the first and most emitting part of making clinker anyway. You're heating limestone to 1,000 degrees or whatever to make the lime. So you've still got the problem of the emissions. I accept that it's then as it's curing, it's absorbing carbon dioxide, but so's concrete actually. A lot concrete over its life will be absorbing carbon dioxide over decades. I mean, never enough to compensate for what has been emitted. But I'd say, yeah, if lime mortar is lower emissions, great. But I find it hard to believe it's that low emissions, given that you have to create lime.
Okay, thank you.
Thank you. Ian. Oh, we've got two Ians. Ian Bounds, please.
My point was something that was put to me by a structural engineer. I was talking about the whole demand for concrete issue. And one point he made that over his career, he said that by the end of his career, relatively recently, a building that was similar to one that might have been built 25, 30, 40 years ago was using massively greater amounts of concrete, partly due to the architectural designs of the buildings. Architects were building bigger single spaces with fewer supports. And in order to do that, they were building these much thicker slabs than would have been necessary with a different architectural approach. And I think his point was that one way of doing it is actually using the minimum amount of concrete that you do need if you're going to use it. And that impacts on, it restricts your design options. And that has not been the trend over the last few decades. The trend over the last few decades has been to use as much as you like to produce what you've seen as the most attractive building. Because concrete has actually been a relatively cheap, simple building material. And we haven't been, sensitized to the environmental impact. I don't know the details, but it was an interesting point that I haven't heard made elsewhere. So.
If I can respond to that, I wasn't aware of that as a trendy, and so that's interesting. But everything else you said is definitely chimes with what I found when I was speaking to the construction industry about this. Much more concrete is used than is actually needed in many structures for all sorts of reasons. One, the standards probably rightly, they're very conservative, but maybe too conservative. But when the structural engineers then design the building, they go then above the standards because it's just easier. Like their time is more expensive to them anyway than cement and concrete, which is actually quite cheap just from a cash point of view. If you forget about the environment. There's and we use, although I've said concrete starts as a fluid, it starts as a liquid, but we tend to use it in these very blocky ways. There could be much more inventive ways to produce the same structural outcome, but with more cleverer shapes. But again, that's kind of expense in terms of labor. The labor's always more expensive, is what people kept telling me, than the actual stuff. So just use more of the stuff. I definitely found exactly everything you've said. I didn't know it had been getting worse, but this is why I think we need limits on carbon in buildings, and then we can use the ingenuity of structural engineers to kind of whatever way is best to reduce the embodied emissions in buildings, whether it's less steel, less concrete, or just thinner designs, whatever. Yeah.
Thank you. I see in the chat that somebody's asked, are we going to discuss further meetings and an ongoing response to Breedon? There is a group that is formed to do exactly that, and I know that there's at least 2 people on that group here at this meeting, and maybe more, because I believe it's got 10 people or so in total. So maybe one of you who's on that group could say when it's going to next meet. Now, Ian, would you like to ask your question?
Hi, I'm a structural engineer, so I come at this from a different viewpoint from most people here. I've also done a lot of research on fire in buildings, especially steel buildings. But in recent years, every structural designer in the country wants to use CLT, cross-laminated timber, in their buildings. And it's nearly always considered in the initial stages of a project. And then it's rejected on the basis of its fire performance. Now, I understand that the Vancouver student residence building has concrete escape staircases, and therefore it's quite easy to get people out of the building fairly quickly. And it wouldn't be 2 hours. People would die in 2 hours. But CLT does react badly to fire. When the lower layer of the cross-laminated slab gets burnt through, or at least gets very hot, it tends to melt the glue that holds it to the upper layers. That means that you've lost a great deal of the strength of the slab in one go. The second layer is useless because it's laminated in the other direction. So you've actually lost basically generally about 40% of the depth of a slab when it's been attacked by fire for a while. And yes, the char does slow down the rate of heating, but it also has zero structural properties. And therefore, the slab starts to deflect very quickly and quite unexpectedly. So one shouldn't minimize the problems of timber construction on a large scale, especially with respect to things like fire.
Thank you, Ian. It sounds like you're really knowledgeable on this specific subject. And whilst I was only reading quoting what the structural engineer had said about the Vancouver building, sounds like you've gone into it so much more detail. And I'm sure that, the report I read didn't mention the glue, and, that sounds a really valid concern. I don't know where he got the figure of having 2 hours to get people out from. Do you have anything to add on this one, Michael?
No, but I think it's really useful to hear from a structural engineer. I mean, I feel quite uncomfortable talking about fire risk really and not knowing anything about it. But it's interesting to hear why, because there has been a lot of interest in timber buildings, but we don't see them going up. So it's interesting to hear that might be the major reason, especially after Grenfell.
Good. Well, thank you very much. The chat, for people who aren't getting it for any reason, is saying that there will be a meeting for the group concerned with Breedon in September, and is asking if there's a contact address for people who aren't on it and who'd like to join. Oops, sorry, I muted myself before stopping. Martin, you have a second question. Do ask that.
Well, it's another comment in that I'm actually sitting within a building which is basically put together with lime mortar, and much of it has lasted for 300 years and is still perfectly secure. So lime mortar probably lasts better than normal building cement.
Yeah, well, I'd come back to my comment about the thing that makes concrete not last is the steel in it rather than the concrete. It gets concrete cancer. So,
yeah.
Yeah.
Yes, I've seen it.
Yeah.
Well, it looks like we've more or less exhausted the questions, which is interesting. I'm surprised, Michael, that you were saying that there is a study that has the wood building having a higher carbon footprint than a reinforced concrete and steel one, because I didn't come across anything like that in the research that I did for this meeting. Many people were sort of saying it depends how green it is, but that it's carbon negative rather than even carbon neutral. But I think that depends on the laminate, the glue and things of the laminate.
Yeah, no, I mean, I was surprised. I'm not saying I agree with that study. I haven't had time to look into it. I'm just, if before I would really kind of want to promote timber again. Well, I mean, I would want to look more into the fire risk, but also into these life cycle analyses. So I think the guy's called Tim Searchinger. I mean, there's various studies about it, and I'm not saying he's having the last word on it, but if you want to find that study, I think I only read the abstract, and he was a big part of the carbon emissions was coming from how he was considering what the land would be used for otherwise, which is a kind of subjective decision. When we measure the carbon emissions of potatoes, I don't think we say, imagine that the alternative is an oak forest, but,
Indeed. And the Zero Carbon Britain report by the Centre for Alternative Technology did have a lot more of our countryside wooded. And you don't have to have wood in plantations. Field boundaries and all sorts of coppices and little bits and pieces, although that does make it harder to harvest. Anyway, we've suddenly got towards the end, 2 people more, so I'll try and quickly get both of them in, but we're coming up to the end, so I'm going to say put an end on these 2. After these 2, no more questions, please, or comments. Andrea, would you like to ask?
So I'd like to just ask Michael about the place in Wrexham which produces Mevocrete, it's called, I think. Is there any reason why they can't build something like that in Derbyshire and use that as a low carbon cement, produce that instead of Portland cement, or doesn't it use lime at all to make that one where you mix it with an alkaline? I don't really know all the technical stuff about it, you see.
I'm not sure, and I'm not sure they even say exactly what the raw materials are. My guess would be that they have some amount of limestone, but just a lot less, and that the main raw material is blast furnace slag. So there's no reason really, except the world is running out of. I mean, the blast furnace slag already nearly all gets used in cement because it's quite a good supplementary material, which is why I say we need to develop similar things to Mevocrete in the long. I mean, they're a great start, but using something like clay, moving on to material that isn't, there's an abundance of. So what there is locally in Derbyshire, I don't know. I mean, I'm not personally, probably unlike a lot of people on the call, I'm not against carbon capture and storage being part of the solution, especially when there's reasonable proximity to storage sites, which there is from the Peak District, compared to, say, the plants in Warwickshire and Northamptonshire. But I know a lot of people disagree with me about that.
Yeah,
you're one of them.
Well, I don't think that carbon capture shouldn't be used, but it's the storing it, transporting it and storing it under the sea that I'm really actually very against, and also feel that yes, we could capture something and do something with it because we use carbon dioxide and other things, and make it that sort of part of the solution, but then the Mevocrete solution be part of it instead of putting all our eggs in one basket with a great big pipeline.
Yeah, I agree. We need a mix of solutions.
Yeah. Thank you.
Must move on. Stuart, would you like to ask the last question, please?
Yeah, I'll just try and be very quick. Yeah, no, I was just going to come back on the stuff that Michael mentioned about the life cycle assessment, and particularly around the kind of comparison of timber and things like that. That's what I do for a job, and there's a huge amount of variation in how you run an LCA and what assumptions you make and what timber you would assume. And I think a lot of the impact when you look at timber is what you assume happens at the end of life. So if you assume that the timber, when it's it grows, it absorbs all that CO2 and it stores all that for its whole life. But then if you burn that building at the end of life or it goes to incineration, then you release all that timber. If you make a different assumption around it, like it goes into landfill and doesn't release the timber for the CO2 for 100 years, then you get a very different answer. So yeah, just to kind of, I guess underline and agree with Michael that what he said, that, you can get a lot of different results from an LCA. It's a useful tool, but it's by no means gives you one result that you can then apply across everything.
Interesting. Can you make a call, Stuart? Is it lower carbon than concrete, or is it just you need to be paid to do the life cycle assessment?
No, I think as we said, obviously avoiding anything old growth or anything like that. If we're talking about land that doesn't have a huge amount of other use, and if we do something sensible with it at the end of life for sensible types of buildings rather than really tall things, I would say it's probably going to be better. I don't know how many caveats that was in there. I hope that was enough.
I would agree with you about the not so tall. We have relatively few buildings that are need to be more than 10 or 12 stories, and why not just put the limit on that? And even in cities like London, you don't need more than 10 to 12 stories, and so that takes away a lot of the problems that the really tall buildings have. Anyway, I'll need to wrap up now. We've run out of time. Thank you all for coming. It's lovely to see you, and really interesting discussion. And we've got quite a break over the summer, but in the autumn we'll be having a talk about zero energy bill homes, but the publicity for that's still to be produced. But simply because you've come today, you'll get it in due course. Thank you again. Thank you, Michael. Thank you, Simon. And thank you, everyone, for coming.
Thank you.
Thanks all.
Thank you.
Bye.
Thanks.